Okay, so the handout for the assignment, you should basically print the code, start reading all of this discussion about the code, which basically discussing what is already implemented, because every portion here, almost every portion says the functionality described here is already implemented by the sample program, right? So this is sample version 3 of this desktop calculator. Okay, so a lot of this discussion took place last week. You can watch the video to refresh your memory on that. Okay, and then it comes down to assignment requirements and what you need to do. So the demo version of Desktop Calculator displays the structure of the AST, Abstract Syntax Tree, which is constructed as a result of successful understanding of the input provided by the user, which is supposed to be an input which can be recognized by the lexer as arithmetic expression. Right? So instead of printing, change the program to evaluate the expression and print the result. Right? Print the result. So helpful ideas. Let's just kind of go through this as through the laundry list. You know that everything is made up of these nodes, right? So the object that stores pluses and minuses and multiplication and all numbers is the instance, like this object in memory, right? This is the instance of AST node class, right? So let's take a look, quick look at AST node class. Right, so our AST node, what it has is, of course, as promised, it has the type field, which tells what kind of field this is, and recognizable types are number, okay, the end of input, which is a technical necessity to tell the caller that the input has ended. The error, which we'll also discuss, that this is a compromise to report errors if we have to. Otherwise, the type will contain pluses, minuses, multiplication, and division characters, which themselves represent the type of operator that the node represents, right? So, for example, we just discussed in the term rule, we just discussed that, for instance, when we encounter a multiplication or division operator, we would like to keep processing this as part of this grammar rule. And what happens is that we simply create an AST node calling the constructor, which basically retrieves the character from the current token, and of course it's multiplication or division, right? So the type of this node right here, the type of this multiplication node present in the tree, which is also the AST node, right, contains the type which basically is either multiplication symbol or division symbol, right? So this is the way the node types which exist there are organized. Okay, so then and of course these nodes that contain numbers, right? The nodes that actually contain the numbers, these objects with numbers, they store this specific type, which is the number. So that's actually character n that's stored for the number. Okay, so our challenge is now to look at this AST node and notice that there are some constructors that are being used by the system, but the operation present here is print, right? So what happens during the print, and this is done, let me see, this is done at the start rule, I think, right? So we say that let's call the expression grammar a rule. If it's an error, we report an error and get out. If it's not an error, we're actually going to say print to the top node. So what happens is that if everything okay, and this is the expression that we were able to parse and construct this specific grammar tree with these 7 different nodes, what happens is that we call print, right? So the AST node supports this print method. And this print method basically says, let's print this. So if we look at the print method, what it does, it basically prints the value, which represents the actual node, the actual value stored inside the node, all right? And then it goes to the left-hand side node and the right-hand side node and says print, right? So the print recursively calls itself, but what happens is that this print results into attempt to print the left-hand side, and then after this is done, print the right-hand side. And likewise, when we say print the right-hand side, it's going to print this plus, and then go ahead and print the left-hand side, and then print the right-hand side. Right? So once this is done, everything returns back, and we go to the left-hand side, which again this node will receive the print request, print method, right? It will print multiplication, and then we'll go ahead and print, say, this node, print your value, which will do, and then print the right-hand side value, which it will do. Okay? So this is the way the print method works. Right, so let's clean up a little bit so that we keep everything visible. And let's go back here. And so it says you need to add your own method called evaluate, which should act exactly or like almost identical to the print method. It needs to recursively its implementation has to be recursive implementation. And so the way I picture it is that, in fact, let me give you a hint, right? So what you need to do is add just one method to solve this homework, all right? And perhaps you can also, instead of calling print, you can call evaluate. What it should be doing here is, of course, it should be returning the double result. Right? I'm expecting that this should be a public method that returns the double, and it should say evaluate, right? So each node here will support the method name evaluate, right? And so in this method evaluate, what I suggest that you do over here is that clearly it should return a double result, because we want to use this as a desktop calculator for the numbers and expressions entered by the user, right? So, and you immediately have to examine the type of node, right? So you know that each node has the type right here, right? So we can basically, you can do if else, or you can just say switch, right? You can switch on the type of the node, which is our data piece right here, right? So each node has the type. So we simply say switch on the type, right? So we can switch on this type right here, right? And then we can go to different case labels. For instance, if this says n, for instance, this is a numeric node, right? Otherwise, right? So any numeric node like this will have the type set to n, because that's what is done during the construction of the tree. Okay, other than actually, instead of hard coding it like this, we actually have the static constant integer that we can use. We can basically change that, but at this point, maybe perhaps this would be a better choice to encode it. That would do exactly the same thing, but we already have static constants here, which declaring the types to be number right there, right? So if this is a number, we know that there is no other descendants, so we can basically convert, essentially the result of this can be, right? is if the current node, where's my AST node right here, right? So if this is a number, all I have to do is basically say return, right? Return, and I have the value, right? But the value is stored as a string, right? So what I can do, I can say double dot parse parse double, right? Parse double, and pass the string to that, and basically have double produce convert the string to an actual double, and that's all I need to do for the numeric type of node, right? So then I can say in case, right? In case if this is say a plus, right? If this is a plus, what I need to do is, there could be two types of pluses, by the way, right? In one instance, plus is binary. If the plus is binary, then both right-hand side and left-hand side will be already set. Remember, the beauty of this tree structure is that it has no errors. If there were any errors or inconsistencies, the processing would have already terminated, and we would have told the user already that, hey, you have a problem. You just didn't follow the rules of arithmetic expression. But if we get to this point that we checked all the syntax and we're able to construct the tree like this, it tells us that this tree is in perfect shape. There's nothing unexpected, and we don't have to worry about any errors at this point. I mean, we could implement some kind of, checks for some unforeseen circumstances. That's a different story. But overall, the health of this data structure is expected to be like 100%. It's not like it has anything unpredictable. So in this case, we can basically say if, right? If, for instance, the node, the left node, right? If the left node is null, right? That means that, let me demonstrate over here. For instance, if I would have, if what I did here, if I, instead of saying 3 times 5, if instead I said something like this, 3 times minus 5, right? So in this case, this minus represents an unary minus, which applies only to 5. So in this case, this 5 would be pushed down. Let me just erase some of this so that we can keep things clean. Okay, so this specific portion, this 5 node, would be pushed down, and instead there would be another node inserted over here with the minus, right? Okay, and so let me switch over here to minus so that we can do the minus processing over here, right? So that would be the case that would be present that we need to work with, right? With the minus in front of 5. So if you can see that if this was an unary operator, the left-hand side of this minus, which we're currently looking at, would be set to null, right? So that's why I say if the left-hand side node is set to null, this, right, this is unary minus, right? And all I have to do is basically return, it's trivial from this point on, just return the value of, right, return the right-hand side node, which is this guy right here, dot evaluate yourself, right? Evaluate will return whatever this thing should be doing to convert itself to a numeric expression, which will basically call itself recursively, right? So this call will arrive at the call of this node right here, right? So basically, if we're looking at this node that has a multiplication or whatever, right? And we detect that this is that this hand side is null, we just simply call evaluate to the right hand side, and this evaluate appears here. It will check the type. Of course, the type of this node is a number, right? So it will happily proceed to return parse double, and hopefully this will return a value of 5, right? But then because this is a minus, and I would like to respect the rules for processing arithmetic expressions, of course I will say minus, right? I will basically take 5 and make it a minus 5 as a result of this expression, right? So that's the way you implement the computation. Okay, so then else, if left-hand side node is not null, all right, if it's not null, then perhaps what we're dealing with is simply this is a binary minus, right? X minus Y, right? So in that case, we just say return return the left-hand side, right? So we can take this left-hand side thing, a left-hand side node, evaluate, right? Minus the right-hand side, the right node dot evaluate. And that's how you implement those things. That's pretty much the logic to follow here. And eventually, I don't know, I mean, you have to exhaust all possible node types. And once you were able to switch on every possible node type, which can be, minus, plus, multiply, divide, plus and minus can be unary or binary, which you can distinguish by looking at the left-hand side, whether it's null or not null. As a result of it, you will be able to essentially chain recursively all calls to evaluate. So basically, the call will come in to say evaluate to this node right here, and guess what plus will do? It will say evaluate this side plus evaluate that side. It's that simple. And the plus will do the magic, because your programming language already knows how to deal with pluses and minuses, right? So if you give it two doubles, and you say plus or minus, your compiler will produce the right code to actually deal with this, right? And basically you need to have a case for, if you're using switch statement, right? You need to have the case for the multiplication. You have to have the case for division, right? And you have to have the case for plus over here, right? I can place it over here, right? So for all of this work, you need to write a very similar code. Since we're not supporting the asterisk or division, the forward slash, as unary operators, we don't have to say if. We should be expecting that both sides are non-null, and so in this case, in case of multiplication, you get the idea. All I have to do is just basically say, hey, return this multiplied by this. Done, right? So for every type of operation that we're supporting in this version of arithmetic expression, I already have my programming language which supports the right type of operation. It can multiply, and it can divide, and it can do pluses and minuses, right? So you get the idea. So this is the way you need to finish. Just add this one method, start calling it, and it'll be doing the magic for you. So think about this challenge, right? So this is the challenge that I want you to think about, and just to keep this compilable for now, I just say return 0.0 at the end, which is basically just to make sure that I can compile this code if I have to. But your switch on all possible node types should exhaust all the possibilities, and if you do that, I can assure you that you can start enjoying the work of your desktop calculator. That's the plan.